This first thing is under introduction of this. They're not important. So you already studied things. What is electrochemical cell? It is just a single arrangement of two electrodes in one or two electrolytes, which converts chemical energy into electrical energy or electrical energy into chemical energy. Okay, there are two types: the galvanic cell and electrolytic cell. The galvanic cell that converts electrical energy, chemical energy into electrical energy consists of two electrodes dipped in two electrolyte solutions, which are separated by a porous diaphragm or connected through a salt bridge. The good example is a Daniell cell. In the Daniell cell, the electrode which possesses a lower electrode potential acts as anode and the higher electrode potential acts as cathode. In all electrochemical cell, the electrode one which possesses a lower electrode potential, we place it left side, and the electrode which possesses a higher electrode potential, place it right side, and the electrode which placed left side usually undergo oxidation and takes negative charge, not positive charge, negative charge, whereas the electrode which undergo reduction takes positive charge. The reason is, in the case of at anode, oxidation takes place. Almost all zinc ions, they migrate into the solution, leaving behind equal number of electrons. So the entire metal surface now takes a negative charge, and these negatively charged electrons are surrounded by a positive metal ion, so that electrical double layer is developed and electrode potential is developed. Similarly, we can observe in the case of cathode, most of the cupric ions, they get deposited over the surface of the metal. As a result, a metal takes positive charge, and this positively charged metal attracts negative ions, so electrical double layer is developed. And that potential developed by each electrode is called it as a single electrode potential, or we can define the single electrode potential is a potential developed at the interface when a metal is dipped in a solution containing its own ion. Okay. This happens mainly due to the difference in the pressure between the solution and the metal. Okay, these are the representation of the cell, galvanic cell. That is usually if the metal undergo oxidation, first we write the metal that gives metal ion, so separated by a single vertical line. And cell representation is a coupling of two electrodes. The anode we should write the left side, and the cathode electrode should be right on the right side. The EMF of the cell is the difference of potential which causes the current flow from an electrode of higher electrode potential to an electrode of lower electrode potential. The standard EMF of the cell is when all the reactants and the product of the cell reactions are in unit concentration or unit activity at 298 Kelvin under 1 atmosphere pressure. So, single electrode potential is the potential developed at the interface between the metal and the solution when the metal is in contact with the solution of its own ion. It is usually denoted by E. Now, the thermodynamic concept of this spontaneous process means a process that takes place automatically without any external air. If a process which takes place only under the influence of an external agency, then it is called it as a non-spontaneous process. The enthalpy, that is a thermodynamic function, it is defined as the sum of the system internal energy and the product of its pressure and volume, usually represented like H is equal to U plus PV, or delta H, change in enthalpy, is equal to change in internal energy plus pressure into change in the volume. Okay, and the enthalpy depends upon the reaction. If the reaction is an endothermic reaction, enthalpy is a positive. If the reaction is exothermic reaction, enthalpy is negative. Then internal energy is the sum of kinetic energy and the potential energy of the substance. Then entropy, it is the measurement of the degree of randomness of energy in a system. Lower the entropy, more order or a less randomness is observed. And usually change in entropy is expressed like delta S is equal to Q by T, reversible reaction. Q is a quantity of heat absorbed by the absolute temperature. Then free energy change. It is what we called it as a Gibbs free energy change. It is defined as the maximum amount of energy available to a system to perform a useful work. It is usually expressed as G is equal to H minus T as it depends upon the enthalpy and entropy. The delta G is equal to delta H minus T delta S, called it as a Gibbs-Helmholtz equation. That is, the Gibbs free energy change is equal to total free energy change of the system minus energy lost in disordering the system. So, Gibbs free energy, or the reaction that decides the change in or the Gibbs free energy. If the Gibbs free energy or the delta G is negative, that indicates the reaction is a spontaneous reaction. If delta G is positive, the reaction is non-spontaneous. So the reaction is, if it is in equilibrium, then delta G becomes 0. Then first law of thermodynamics, that is called it as the law of conservation of energy. That is, energy neither be created nor be destroyed. So usually it is represented as delta U is equal to Q plus W, or delta is equal to Q minus W when the work done by the gas. Then in such a case, you can take it as a Q minus W. The second law of thermodynamics, that is the entropy of an isolated system always increases, or the entropy of the universe always increases and never decreases during the course of any reactions. We can write it as delta S is equal to Q by T. EMF of the cell, it's already defined. The difference in the cause of flow of current from an electrode of higher electrode potential to an electrode of lower electrode potential. Then we can represent the relation between free energy change and the electrode potential. It is in an electrode, the work that taking place is always negative, because the decrease in free energy, or the free energy is related with the work. That is, decrease in free energy is equal to maximum useful work that taking place in the system. That is, delta G is equal to W. The electrode process that taking place in the the work that taking place in the electrode is the carrying with the potential of E volt, carrying electrode n number of electron with the F Faradays of current. Okay, that can be represented as W is equal to NFE, or delta G is equal to minus delta G is equal to W, because in an electrode, the reaction is a spontaneous. The decrease in free energy of the system is equal to maximum useful work done by the system. So we can write it as a minus delta G is equal to NFE, or the change in free energy is equal to minus NFE, where E is the electrode potential, or you can represent it this one for Ecell potential. It becomes delta G is equal to minus NFE cell. Then Nernst equation. Nernst derived a quantitative relationship between the electrode potential and the concentration of the electrolyte species involved. First, we'll consider a reversible reaction, M giving rise to Mn plus n number of electron. By conventions, we can take reduction reaction is the forward direction. So Mn plus n number of electron equal to M. From thermodynamic consideration, we can write decrease in free energy related to the equilibrium constant by the equation minus delta G is equal to minus delta G naught minus RT ln K, or delta G is equal to delta G naught plus RT ln K. The decrease in free energy of the change when reactant and the product of the reactions, if it is in a standard condition, then it is represented as a delta G naught. Equilibrium constant K is equal to concentration of M by concentration of Mn. Then the work that taking place in the system or the cell or the electrode is W is equal to minus NFE, or delta G naught is equal to minus delta G is equal to W, or we can write delta G equal to minus NFE, or delta G naught equal to minus NFE naught. These equations can be introduced in the thermodynamic equation. We can write it as minus NFE is equal to minus NFE naught plus RT ln concentration of M by concentration of Mn plus. Divide by, throughout the equation is divided by minus NF. We can write E is equal to E naught minus RT by NF ln concentration of M by concentration of Mn plus. So we can write converted it into 2.303. So we can write it like this. We can write this one. E is equal to E naught minus 2.303 RT by NF log concentration, log 1 by concentration of Mn plus. So final electrode potential can be represented as E is equal to E naught plus 2.303 RT by NF log concentration of Mn plus. This is what we called it as a Nernst equation. Similar way, we can represent the Nernst equation for a cell potential. For a cell potential, the equation becomes E is equal to E naught plus 2.303 RT by NF log concentration of reduction species by concentration of oxidation species. Okay. Where E naught is the electrode potential at the 1 molar concentration when all the reactant and product are under standard condition. Then types of electrochemical series. Electrochemical cell. There are two types of electrochemical cell. Three types of electrochemical cell: primary cell, secondary cell, and concentration cell. If the cell reactions is not reversible, called it as primary. If the cell reaction is reversible, then it is called a secondary cell. The concentration cell is a one. An electrochemical cell is formed by the combination of same electrode dipped in a same electrolyte solution of different concentration, called it as a concentration cell. Here the electrodes are same, only the difference in the concentration is observed. Again, while choosing anode and cathode, the one which possesses a lower electrolyte concentration act as anode and the other one act as a cathode. This is an example for a concentration cell. Silver coupled with the silver is dipped in a silver ion solution with a concentration 0.01 m at act as an anode. It is coupled with the silver dipped in a silver nitrate solution with a concentration 0.1 m act as cathode. And the anode and cathode reaction it just appears like a transfer of ion from an electrode of higher electrolyte concentration to an electrode of lower electrolyte concentration, but it takes place through electrochemical reaction. We can represent the Nernst equation for a concentration cell. So we can represent Nernst equation for a left cell, left electrode, that is E naught equal to E naught plus 2.303 RT by NF log C1, E right equal to E naught plus 2.303 RT by NF log C2. And Ecell is E naught right minus E naught left. Finally, we can get Ecell equal to 2.303 RT by NF log C2 by C1. Here, C2 is always greater than C1. Then only we can get a positive EMF. So, in concentration cell, the electron with the lower electrolyte concentration act as anode and that of higher electrolyte concentration act as cathode. Then types of electrode. There are 6 types of electrode. Metal, metal ion electrode. When a metal is dipped in a solution containing its own ion of the metal, then it is called as a metal ion electron. Like zinc dipped in a zinc ion solution, copper dipped in a copper ion solution, silver dipped in a silver ion solution. Like metal salt ion electrode. When a metal, in this electrode, a metal is in contact with the sparingly soluble salt of the metal ion, which is in equilibrium with the solution containing the same ions of the sparingly soluble salt. A metal is in contact with a sparingly soluble salt solution containing anion of the salt. So example is a Calomel electrode or a this one silver electrode. Then gas electrode. It consists of a gas which is bubbled on an inert metal or a wire, platinum-like, immersed in a solution containing ions of the gas molecule. Metal usually provides an electrical contact and facilitates the establishment of equilibrium between the gas molecule and its ions, like hydrogen electrode. Then reduction electrode. The reduction electrode is one with the potential arises by the presence of oxidized and reduced form of the same substance in the solution. A potential developed is usually put up by an inert metal. Example is platinum is in contact with the ions like Fe2 plus and Fe3 plus, platinum contact with Cr plus 6 and Cr plus 3, etc. Amalgam electrode is similar to metal ion electrode. In metal amalgam, which is contact with the solution containing its own amalgam. Metal amalgam is contact with the solution containing its own ion. And ion-selective electrode, generally called it as a membrane electrode, which is capable of exchanging a specific ion with the solution with which it is in contact. Then reference electrode, and electrode potential is known, which is reproducible and stable, can be used as a standard reference while measuring the single electrode potential of any other electrode. There are 2 kinds of reference electrode, primary reference electrode and the secondary reference electrode. The primary reference electrode is the one in which the electrode potential is set to 0, and the secondary electrode potential is a potential in which the electrode potential is determined on the basis of primary reference electrode. The next is construction and working of Calomel electrode. In the Calomel electrode usually consists of a narrow glass tube. A mercury is placed at the bottom of the tube. Above mercurous chloride paste is introduced, and the remaining portion is filled with the KCl solution. A simply platinum wire is inserted in the middle of the mercury, which is used for electrical contact. And this is placed in, it may be placed in an inside an outer cover with the, which is filled with the KCl solution. Representation: mercury is in contact with the mercurous chloride, it in turn contact with the chloride ions. The calomel may act as anode or a cathode. When it acts as an anode, oxidation reaction take place. That is, a mercury interact with the chloride ion, forming mercurous chloride with the liberation of 2 moles of electron. When it acts as cathode, mercurous chloride takes electron, forming mercury and chloride ion. The net reversible reaction is mercurous chloride takes electron. When the forward reaction is a reduction, forming mercury and chloride. Backward reaction becomes oxidation. The electrode reduction electrode potential of calomel electrode can be represented as E is equal to E naught minus 2.303 RT by F log concentration of Cl minus to the power 2, or we can represent that the electrode potential, we can come to know that the electrode potential depends upon the chloride ion concentration. By introducing different concentration, we can get a different potential. Like when we introduce 0.1 normal KCl, potential developed is 0.334 volt, 1 normal 0.281, and saturated is 0.2422. Usually in the reference electrode 0.2422 volt is developed because we use the saturated KCl solution. Advantage: simple to construct. Cell potential is reproducible and constant over long period. Cell potential does not vary with the temperature. Demerits: it is used if it is used above 50 degree, the electrode may becomes unstable, and it is used as a secondary reference electrode while measuring the single electrode potential of any other electrode. So to determine the single electrode potential, usually that electrode is connected to the Calomel electrode and through voltmeter, and EMF is determined by potentiometric method, and by using the standard equation EMF is equal to E cathode minus E anode, we can detect the electrode potential of any electrode by knowing the value of Ecell and the electrode potential of Calomel electrode. Then ion-selective electrode. An ion-selective electrode is the one which selectively responds to a specific ion and develop a potential at the electrode in a mixture is a function of the concentration of that particular ions. Particularly glass electrode. The glass electrode consists of thin-walled glass bulb made up of a special type of glass with a high electrical conductance. Then the bulb is filled with a 0.1 normal HCl solution. Simply silver chloride electrode is inserted in the middle of the bulb, act as internal reference electrode, and it is connected to platinum wire for external electrical contact. And that electrode is dipped in a solution whose pH is to be determined. Then electrode representation is silver is in contact with silver chloride, in contact with chloride ions, in contact with the standard 0.1 HCl solution with the glass. When it is dipped in the solutions, we can observe this one. Reference electrode is in contact with external analyte solution with the concentration C1. In turn, the membrane develop a potential. Outer membrane develop a potential of E1 volt, and the inner membrane, inner wall of the side of the membrane develop a potential E2, which is in contact with N by 10 HCl. In turn, in contact with the silver chloride electrode. Due to difference in the difference in the concentration of H plus ion inside and outside the glass bulb, give rise to boundary potential across the membrane. So boundary potential EB is represented like a 2.303 RT by NF log C1 by C2, where C1 is the concentration of H plus ion of the solution into which the glass membrane is dipped, and the C2 is the H plus ion acid solution inside the glass bulb. So we can represent the C2 is a constant. We can represent this one is a EB is equal to constant plus 2.303 RT by F log C1, because N is equal to 1. So EB becomes equal to L plus 0.0591 or 592 log C1, because the constant L is equal to minus 0.0592 log C2. Then EB is equal to L minus 0.0592 pH, because pH is equal to negative logarithmic to the base 10 of concentration of H plus. So EB depends only on the concentration of H plus. But the glass electrode potential is the combined potential of the two terms. The one is a boundary potential, other one reference electrode potential and asymmetric potential. So the asymmetric potential is a small potential developed even when EB is even when C1 equal to C2. EB is it should be becomes 0 when C1 equal to C2. But in actual practice, so even C1 equal to C2. EB is not equal to 0, and that potential what we called it as a symmetric potential. So we can represent EG is equal to L minus 0.0592 pH plus E reference plus E asymmetric. All the constant term together we considered as a standard electrode potential of a glass electrode. We may represent EG is equal to E naught G minus 0.0592 pH. Okay. The advantage can be used in oxidizing or reducing atmosphere. Electrode does not get poisoned by using special glass electrode. pH 14 up to 14 can be measured. Limitation: special glass electrode can measure up to pH 12. Above pH 12, cations of the solution affect the glass interface and renders the electrode useless. In acidic solution, pH less than 1 salt effect due to anion is observed. Because of high resistance of a glass, it is necessary to use a special electronic potentiometer. Then determination of pH using glass electrode. So here the glass electrode is coupled with the Calomel electrode, and the pH of the solution is determined by using a standard equation Ecell equal to E cathode minus E anode. By convention, Calomel electrode is taken as a anode. So we can represent pH equal to E naught G minus E standard Calomel electrode minus Ecell by 0.0592. Then energy storage system. So in the energy storage system, we come across the types of battery. The battery is a battery consists of two or more cells connected in series or a parallel or both to obtain a higher potential. A spontaneous redox reaction forms the basis of in all battery. If the cell reaction is not the classification, if the cell reactions are not reversible, then that battery is considered as a primary battery. Only electrical energy is produced only if the active materials are present in the cell. The good example for a primary battery is zinc manganese dioxide battery, lithium manganese dioxide battery. In primary battery, the cell reactions are not reversible, so that is not recharged or reused. The secondary battery means secondary battery in that the cell reactions are reversible and rechargeable. These are also called as accumulators and or the storage cell. The electrical energy is stored in the form of chemicals and utilized for supplying the current when it is needed. The active materials can be restored at the respective electrode on recharging. The charging and recharging cycle can be repeated. The good example for secondary battery is a lead acid batteries, nickel cadmium battery, nickel metal hydride, lithium ion battery, etc. And the third category of battery, what we call it as a reserve battery. Here, the battery usually stored in an inactive state and made ready for use by activating them prior to their application. The good example for reserve battery is a magnesium water activated battery or some thermal active battery. Here, the key component is separated from the rest of the battery prior to the application. Usually, electrolyte component is isolated from the electrodes and it can be stored for a longer time and they possess a high or a good shelf life. They can be designed to meet extremely long and environmental storage requirement. Water or heat may be an activator. In water activated batteries, the electrolyte usually taken in the solid state and water is added for activation. Then nickel metal hydride battery. I'm sorry, I'll take one minute. Hold on. Below my this one PPT is visible, is it? It's not visible. Excuse me. Without PPT, I explained. Is it? Am I audible? Without PPT or with PPT? Presentation mode. Is it in the presentation mode only? Before it's not visible. Okay. Then it's okay. Okay. The next one type of battery, that is a nickel metal hydride battery. In the nickel metal hydride battery, the anode material is a hydrogen, which is in the form of metal hydride, such as vanadium hydride, zirconium hydride, titanium hydride, which is stored in the form of which is stored in the using alloys like a lanthanum nickelates, which is coated over the surface of metal hydride. Cathode is highly porous sintered nickel substrate, which is impregnated with the active materials like nickel oxyhydroxide. KOH act as electrolyte. Polypropylene is a separator. The representation is metal hydride is in contact with KOH, in turn contact with nickel hydroxide and the reactant nickel oxyhydroxide. The reaction can be represented like anode reaction is metal hydride interact with hydroxyl ion forming metal, water and liberation of electron take place. Cathode, the electron is consumed in the presence of water by nickel oxyhydroxide forming nickel hydroxide. The net reaction is metal hydride combined with nickel oxyhydroxide forming metal and nickel hydroxide. Potential produced is 1.35 volt. Application, it can be used in the cellular phone, computer, total electronic equipments. The next type of battery is lithium ion battery. In the lithium ion battery is suitable for mobile devices, for small size, lightweight, high performance, high energy, high voltage. Lithium ion battery is lithium cobalt oxide battery. In lithium cobalt oxide, lithium intercalated with the graphite act as an anode, which is connected to a copper foil which act as a current collector, and the cathode is made up of lithium cobalt oxide with the aluminium foil as a current collector, and they are separated by means of a polypropylene separator. And the organic solvents lithium lithium salt solvents are used, which is dissolved in an organic solvent, polypropylene carbonate or ethylene carbonate, etc. Then usually stainless steel containers are used. Reaction that taking place in a lithium ion battery anode, lithium carbide, LiXC6, giving rise to X moles of lithium ion with X moles of electron and X moles, 6 moles of carbon. This liberated lithium ion and electrons are consumed by a lithium an active material present at cathode, that is lithium cobalt oxide, forming a stable lithium cobalt oxide. And the cell reaction is just, it is a trapping of lithium ion in the presence of or the electron or reduction take place. That is a lithium LiXC6 plus Li1 minus XCO to giving rise to lithium cobalt oxide plus 6 moles of carbon. The potential developed is a 3.6 volt and it is usually used in laptop, aerospace application, cardiac applications, etc.